Hello everyone, my name is André Pedersen. I'm a PhD candidate in medical technology at NTNU in Norway. My research focus is on the application of artificial intelligence in digital pathology. I'm part of a multidisciplinary team of researchers, engineers, and medical doctors within the fields of pathology, oncology, and surgery. We are currently developing a platform intended for use in digital pathology. This platform I will present for you today. This is the outline for today's talk. I will start by explaining the difference between conventional and digital pathology, go through some challenges and proposed solutions, demonstrate the platform, and summarize current features before I conclude. In conventional pathology, the pathologist examines a section of tissue in a microscope. The section is prepared in the lab in several steps. For most pathologists, the main task is to diagnose and examine cancer. The diagnosis from a pathologist often guides the treatment that cancer patients receive after surgery. In digital pathology, however, the section is scanned, and the pathologist uses a computer screen for diagnostics instead of a regular microscope. This has several advantages and potentially some limitations. One great advantage is that it enables the use of artificial intelligence as a tool to assess the section. Now over to some challenges. As the images used in digital pathology are giga-resolution sized, as seen from this example here, proper memory management is a substantial challenge. Convolutional neural networks is the current state-of-the-art method for most image analysis tasks, but in most open-source platforms, deployment of CNNs is not possible. There exists a variety of different scanners that all have their own unique image formats, which is a challenge when reading hosted images. Implementation of digital pathology also takes time because pathologists have a hard time letting go of their beloved microscopes. Thus, to make the transfer easier for pathologists, a digital pathology platform should be intuitive and easy to use without the need of really understanding anything about what is happening underneath. Remember, pathologists are not technologists. But in the same way, technologists are not pathologists. To provide the optimal solution, working directly with the pathologist, such as we're doing, helps us ensure that we make the platform user-friendly, especially in the eyes of the pathologists. As an example, I will use this small region of a whole-side image of lung cancer. Now, images of the size of whole-side images cannot be stored directly in memory, and thus these images are commonly stored as image pyramids. The overall idea is to store several downsampled versions of the same image. That way, if one wants to visualize the overall section or run some algorithm, one could use one of the lower resolution planes. Now, let's just choose one downsampled version as an example. Even on high-end systems, state-of-the-art CNNs can only input images of size up to 2000 squared pixels. Thus, the image we chose to use is too large to be used with the CNNs. However, downsampling further might result in too much information lost to solve the task at hand. Thus, the most common solution is to tile the image, that is, to subdivide the image into smaller regions and stream each tile individually through a network or algorithm and stitch the result. This is a toy example of how such a result might look like. Note that the regions here that don't contain any color, that is due to us filtering out glass beforehand. So this is an example of how such a pipeline might look like, and also note that the neural network module could literally be anything. Over to some proposed solutions. The example seen on the previous figure is actually an example of something called a FAST pipeline. We chose to use the open source framework FAST for the implementation as is implemented in C++, designed for processing and visualizing medical images, and also has a solid foundation in deployment of CNNs. For handling different image formats, we are using the open source C++ library OpenSlide, as it handles most common formats and enables us to read tiles from image planes without loading the entire whole-side image in memory. For reading, processing, and rendering whole-side images, we are using the concept of virtual memory systems. Enables us to only load tiles from disk necessary at a given time, thus saving memory usage. This required us to implement a lot of backbone code from scratch using OpenCL and OpenGL. Since we are processing and rendering, we're using two different memory systems handling both RAM and GPU RAM. In rendering, to further reduce memory usage, we are compressing textures, for instance, for high-res segmentations and bounding box detections. Now, to deploy CNNs, we chose to implement inference code using TensorFlow, OpenVINO, and TensorRT, as they're all implemented in C++ and are already made available through FAST. To handle quite different architectures and tasks, we chose to implement handlers from scratch, assuming some structure on the inputs and outputs of these architectures. FAST automatically chooses which inference engine to use, depending on which inference engine are available on your machine and which model you have selected. As we are a multidisciplinary team, we have focused a lot on making the platform's UI user-friendly. Currently, running inference only requires a single click. The GUI is also made to be simple and intuitive. There also exists message prompting, informing, guiding, and warning the user. In order to set parameters and customize pipelines, there has been added text pipelines in FAST. That makes it possible to define and run pipelines directly from a text file. To make the analysis scalable, we have introduced a popular concept of projects that makes it possible to add hosted images essentially to a bag and stream each hosted image through some method and save the result. With project, it also makes it possible to load these results later on. In order to make the CNN module more generalizable, in FastPathology, we have chosen that each model should have a corresponding text file that essentially says something about how the model should be handled, for instance, during rendering. And now I'm just going to show you a very little demonstration. In this demo, you can see me just choosing some hosted image. On the left, you can see how the GUI looks like. You have different options for handling processing and rendering. You also have options for running pipelines and editing them yourself, creating, opening projects, etc. Here you can see me zooming in on the hosted image. As you can see, it's quite fast. You immediately get access to the region you're trying to study. Here I'm applying some very simple glass filtering method before applying some patch-wise classifier model. And as you can see from the view section, I'm able to choose which results to show, both using toggling and changing the opacity. And there also exist other types of models. This one performing semantic segmentation on low resolution before applying patch-wise classifier model within this segmentation. And here, of course, you can also see me toggling the classes. Now over to another example. This is me performing bounding box detections of nuclei. And as you can see, it's running extremely fast because it's a very lightweight model. And now as I zoom in, you will actually see the bounding boxes much clearly, as you couldn't see before, because we were compressing the textures quite a bit. And here is another example of me doing a similar analysis, but this time I'm doing higher resolution semantic segmentation of nuclei. And as you can see, this is also possible and working quite well. Here I'm changing which results to show, and here I'm just showing with and without the nuclei. Yes. Now, this is an overview of the current features that exist in the platform today. Most of these I've been through, but I could also highlight that we actually have an integrated pipeline editor that makes it able to change parameters and all that. So in the end, we have developed FastPathology, which is an open source cross-platform software for AI-based digital pathology. It brings state-of-the-art deep learning-based solutions in reach and easily accessible for the pathologists. We have also extended FAST to better support software development for digital pathology purposes. The project is continuously in development. We encourage the community to contribute to both of these open source projects on GitHub. Finally, I want to thank my research group and our collaborators nationally and abroad. I also want to thank the License Committee and Kreftfondet for funding this project. Thank you very much.